The derivative. I know it's been a while, but this is what we were doing last time. We talked about new stuff. The Brzezowski derivative. I don't know if you have any recollection of this, but this is what we were discussing, I guess, on Tuesday last week. The derivative. This eventually, and probably we'll get to it today, is going to tie into something relevant about showing that a language is not regular. Remember, regular just means it is the language of some NFA or DFA or regular expression. But some languages are not regular, and you can demonstrate it using the derivatives. But maybe I'll just refresh our memory first about what it means. So if for some language L, the derivative with respect to A of L, where A is like one of the letters in the alphabet, the definition of this is it is all x such that AX is in L. So it means you take all the strings that were in your language that start with A, and you remove that A, and you give me whatever is left over. So like the derivative of just sort of an ordinary string of, well, I shouldn't say that. How about this? If what if L was the language A, B to the N? So here, the language consists of strings that look like A followed by a bunch of B's. When I take the derivative of that, what it means is you get the same strings again, but you take the A off the front of them. And so in this case, the derivative is just B to the N, right? You take any string which originally started with the A, and you remove that A, and you give me what's left over. What is the derivative with respect to B of that? This would mean you take any of those strings which started with a B, you remove that B, and give me what's left over. What would you say for this one? No. This is removing a B from the front. Yeah.
Is it like nothing?
It's nothing. Yeah, it is the empty set in this case. You know, writing the definition here, remember it says all x such that AX is in L. So this means all, where in this case I'm using B instead of A. So this means it's all x's where BX is in the original language. That is, you take strings from the original language that start with B, you remove that B, and you give me what's left over. But there are no strings in this language which start with B. So you get the empty set. That's it. All right? How about this one? Here's a fun. You basically just take the A's off the front, right? If I had something like derivative of AB to the N, AB to the N, then the answer here is just B to the N, AB to the N. Right? Yes?
Is it only like the front of the string?
Yes. Yeah. The left side you do this to. Yep. I suppose if you wanted to, you could define a derivative that works on the right side, but the left side is more appropriate for what we use the derivative in order to do. You'll see why. It matters that you're using the left side rather than the right side. Here's another example. These all look sort of silly, I suppose. Very simple. What do you think? What is the derivative of just A to the N?
N is greater than 1.
One.
A to the N.
I hear a lot of A to the N. A to the N minus 1. I also heard A to the N such that N is greater than 1? Greater than or equal to 1? I think that's probably what you meant. Actually, it's not the second one. This is not quite right. And in fact, that also means Well, the first one kind of is right, although why this is right? This says it's a to the n's where the n has to be. You have to use at least one of the n, at least one a, right? I can't speak anymore. I haven't taught for over a week. New material. This actually is not right though. For example, this set, the derivative of this, it does contain the empty string, because the empty string is what you get if you started with just a and you remove that a and you give me what's left over. It's the empty string. So the answer here, whereas this says it's L powers of a, but not the empty string. But actually, the empty string is part of this language here. A to the n minus 1, I get why you would say that, but that's actually kind of a strange way of saying this answer. There used to be, I mean, the reason you would say it is there used to be n a's, and they took one away, so now there's n minus 1 a's. But as a set, what this means is just all strings that look like some power of a.
It would just be a to the n again.
Yeah, I think the clearest way to write this is just a to the n again, all right? Although this is not, I wouldn't say that's wrong, although it's a little strange to write it in this way. So I would say, okay, but strange. No offense. It's a little suspicious if, when I write this, I always allow for n to equal 0 possibly, but you can't when n is 0, this doesn't really make sense. So I would say the true, answer is just this. And this is what I said, this one's a little weird. It's that. If you start with any string which consists of a bunch of a's, and you just take one of the a's away, what you get is still the set of all strings which contain a bunch of a's, right? Somewhat strange, I suppose, but it's true. How about this? Here's another weird one. You start with everything that looks like ab to the n, and you remove a from the beginning. What do you think? Yeah. B a to the n? Is that what you said?
Yeah.
That's something. I don't know. So like, for instance, this language here contains some things like AB, 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 right? And then after you take the derivative of that string, you end up with, you sort of X out the A on the front, and you get BA, BA, BA. So that's, what do you think?
B, A, B to the power n.
Yeah, this is very strange looking, but this is the correct answer. B, A, B to the n. If you just look at the set notation, it looks like the strings actually got bigger, but they didn't. All I'm saying is, if you start with some power of AB, some repetition, AB, 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 and then you take away the first A, what you're left with is a B followed by another repetitions of A's and B's. All right? Yes?
So, is it not right to have like the BA to the end sort of thing?
BA to the n. No, that...
Like that whole group, like BA and that whole thing.
Yeah, I see what you mean. This, I believe, is the same set as BA to the n B. Yeah, those are the same. Although, I don't know, for some reason the first one seems clearer to me, but those are equal to each other as sets. So those are both correct. Yeah. It's just a bunch of alternating B's and A's where there's an extra B. You can say the extra B is at the beginning, or you can say the extra B is at the end. Yeah, great. All right, so the derivative, I'm just trying to say it's not a very complicated idea, but when you write the sets, sometimes it looks weird when you write it. Somewhat counterintuitive things can happen when you write the sets like that. All right, I'm going to make it a little weirder, although not much. You can take the derivative with respect to individual letters. Here I was doing derivative with respect to A every time. Of course, you can also do derivative with respect to B. But in fact, you can also take the derivative with respect to any string. So for any string x, you can do derivative with respect to x of L. And what this means, it's the same. It's all, well, it's all S in L such that XS is in L. What? I wrote too many things here. It's all S. I'm trying to just copy this definition I wrote up here, right? X such that AX is in L. It's all the strings where if you stuck an A on front of them, they would be in the language. This is the same thing. It's all the strings. I can't use X twice, so I had to call it S. It's all the strings S such that XS is in L. All right, so instead of just removing a single letter from the beginning, I'm removing an entire string from the beginning of those strings. So, for example, I can do something like D, A, B of AB to the n is AB to the n. This is, again, slightly weird looking, but it says if I have a bunch of AB, AB, and taking that derivative will remove an AB at the beginning. And what remains is just still a bunch of a power of AB. All right. You could also do something like this. This is a little slightly more interesting for this example. Derivative with respect to ABA of AB to the n. This means you have a big string that looks like a bunch of ABs, and I remove ABA from the beginning. What's left?
Is it the BAB? Like
B, AB to the n. Yeah, great. You took off some AB, and then you took off an extra A, so there's a B left over, followed by some more powers of AB. Yeah, great. Or how about something like this? D, derivative with respect to A squared of AB to the n is the empty set. Yeah, remember, if there are no strings that actually begin with that thing, you get nothing. The empty set. Great. All right, this is the Brzezowski derivative. Let's talk about what it is good for. Oh, I had this written in my notes. I better say it. If we're talking about English words, I thought this was cute. If E is the set of English words, what is this? Derivative with respect to bop of E. Anyone give me anything that would be in this language? All English words, derivative with respect to bop. It means you take a word that starts with BOP and you remove BOP from it. And then you tell me what's left over. There's one easy one. And, yeah?
Wouldn't it just be the word bop? And then there's nothing.
Yes, so the empty string is one. That means the word bop is a word, and you cancel the BOP off of that, and you're left with the empty string. All right? I actually, I did a search on my list of English words file for this. I also got per, because bopper is a word. B-O-P-P-E-R is a word. And then I also got pers, and I got head, bopped is a word, and ping, because bopping. And there's one more, it is the letter S, because bops is a word. All right? This is the full list when I used my my list of English words. All right? Excellent. I hope that was enlightening. All right, this is the derivative. First of all, you have to find all the words that actually do start with BOP, and then you take the BOP away, and you say what's left over. All right, that's the derivative. Okay, what is this good for? It is good for something, actually. I would like to refresh your memory. Here's a DFA that I drew when we started talking about this. I'm just going to draw it again. I'm going to call it M. It's slightly complicated just so that we'll have enough to talk about. The language of this thing, as I'm drawing it, it's ab cubed to the n. You have to do a to get to the accepting state, and then once you're there, you can do multiples of 3 b's to get back around to the accepting state. And then everything else is a failure. This is a DFA. So this with the A, this with the A, and there's one like this with the A, and this is a failure state down there, all right? So the only way to be accepted here, I think it's clear what I said about the language, is if you start with an A and then you follow that, if you want to, by some multiple of 3 b's, all right? Now, I'm going to give names to these states too, if you don't mind. Sorry, I should have done this before. I'll call this S, T, R here, and then X, Y, these ones. The derivative comes up in this context when you ask the somewhat strange question of what happens if I move the starting state of my DFA? If I move the starting state, how does that change the language? If I move the starting state instead of S to T, I think you'll see what this has to do with the derivative. If you start here instead of starting back here, if I start at T instead, it means I no longer have to do this A at the beginning, all right? And so the language here, it's the same, only that initial A, you can just leave it out. And you get actually the rest of it. So if I move the start state to T, then the language, L, becomes just b cubed to the n, right? That A goes away. You no longer need to do that first A. And, this is not a coincidence, that happens to be equal to the derivative with respect to A of the original language. And it's an A here because I shifted the starting state by going through this edge, which was labeled with an A. All right. So the basic principle here is if you move the starting state through a particular letter edge, this will change the language by doing that derivative. So this is the moral of the story. Moving the start state through an edge labeled A changes the language into the derivative with respect to A of whatever you started with. All right? I hope you're convinced by looking at this particular example. What if I shift it by going through a B here? What if I go down here to X? Then I should expect the language to be the derivative with respect to B. So if we move the starting state to X, sorry I have to scroll away from the picture there, then the language should become the derivative with respect to B of my original language. Now, the original language, remember, was AB cubed to the n. And so what is the derivative with respect to B of that? It is the empty set, because none of those strings begin with a B. All right? That means when you move this, apparently, if you move the starting state to X, then no strings will be accepted by this machine anymore. And is that actually true? Actually, it is true if you look at the diagram. If you were to start here, then there are no accepted strings. There's no way to get to the accepting state from here. All right? So it all kind of checks out. And in fact, you can move the starting state even like to R by going through the A and through the B. All right? So actually, it's not just one edge at a time. Moving the starting state through any path along here corresponds to doing a derivative of a string, right? If I went from S all the way to R, that would be the derivative with respect to AB, because I went through those two edges at a time. Okay, so I will say, when I do this, where x is some other string, this corresponds to moving the starting state through several edges. I'll say, spelling out the string x. Right? Whatever that x is, if it's, ABA, that corresponds to a motion, moving the starting state through a and then a B and then a A. All right? It's kind of, this works better on DFAs than NFAs, because on NFAs there may not be edges and there's epsilons you have to worry about. I don't want to get into that. All right? So, this corresponds to moving the starting state through several edges that spell out the string x. All right? Great. I hope everybody agrees. Now, I want to say something interesting about this. What does this have to do with regular versus non-regular languages? I'm going to copy this. Whoa. I cut it. I didn't want to cut it. Picked up the L too. You get sort of an interesting fact, kind of for free, in this particular example, where L of m was a b cubed to the n. Although you don't even have to know what the language is here, I can tell immediately that the derivative with respect to a of L of m, it must equal the derivative with respect to a b cubed of L of m. Anybody have thoughts about this? How do you know that's true? Even if you don't, I'm going to erase this, because this actually has nothing to do with knowing what the language is. Yeah?
Because when you do the moving of the state, you'll end up in the same place.
Yeah, right. So this one here, derivative with respect to a, that is the language that you'll get if you shift the starting state to t through this edge a. All right? This over here is the language you'll get if you shift the starting state by ab cubed, which is also to t. So these actually, they must be the same as sets. They must be equal, because they both are the language accepted by this machine when you start at t. All right? Okay, that's kind of interesting, I guess. Now, in fact, there's only 5 states here, right? That means there's only 5 possible choices of where the starting state could possibly be, which actually means all the different derivatives you take, there's only 5 possibilities for what the answer could be as a set. This is not obvious at all, but it's just naturally because taking a derivative is like moving the starting state, and there's only 5 different possible starting states, so it means for this language, this is sort of a strange but true fact. For this language, there are only 5 possible derivatives, d by dx, for various x. Even though that x could be anything. There are infinitely many different choices you could make for the x, but when you take those derivatives, there's only going to be 5 different answers. Those different choices for x, they eventually lead to the same 5 different possibilities. Yeah.
I have a question about the problem that we did on this. So, what would the set be for the language of AB?
The derivative of AB?
Yeah.
I thought I wrote that down. I guess I didn't. It would be, can we just, as a little sidebar here, derivative with respect to AB of, my language is a b cubed to the n. Yeah, what is that? This is a good little homework problem or something. You're doing the derivative with respect to ab. That means you cancel the a at the beginning and then one more b. And so what's left over? I guess there's going to be 2 more b's, which used to make up a block of 3, and then some more blocks of 3. So I would say b squared b cubed to the n. Something like that. There's other ways you could write that, I guess, but that's, yeah. All right. Anyway, for this language, there are only 5 possible derivatives for various x's. That's what I wanted to say. Now, what does this have to do with regular languages? This is kind of a surprise theorem. It comes out of nowhere, sort of, but it's actually super useful and kind of deep. If some language L has a DFA for it, there must be only finitely many derivatives. Because the DFA has finitely many states. And however many states there are, those are the only choices for where you could shift the starting state to. And therefore, there are only so many different derivatives that you could get. All right? If some language has a DFA, there must be only finitely many derivatives. And that is actually pretty easy to check if there are finitely many or infinitely many derivatives. And this is how you can show that something either does or does not have a DFA. So I'm going to write this I'll write this as a big theorem, which we're not going to do the proof, but it's basically just because of all the stuff that we've been saying. Rather than saying if some language has a DFA, I'm just going to say if it is a regular language. So if L is regular, then it has only finitely many derivatives. Actually, this is an if and only if, but we're only going to really use this version of it. In fact, what we're going to use is the contrapositive of that. Anybody remember your discrete math? Can you say the contrapositive of this? This is a if-then, right? P implies Q. Anyone remember what the contrapositive is? You think?
Is it like if there's infinite derivatives and it's not regular?
Yes. Yeah, the contrapositive would say not Q implies not P, and it is logically equivalent to this. So if I say if you believe this theorem, it is the same as what I'm about to write. It's contrapositive, which is what he said. Not Q implies not P. In this case is if there are, I'll say not there are. If L has infinitely many derivatives, then L is not regular. And this is the way to prove that something is not regular. You demonstrate that it has infinitely many different derivatives. And in most examples, that's pretty easy to do, actually. You don't have to try too hard to do this. If L has infinitely many derivatives, then L is not regular. Let's try some examples. I want to do my favorite example of a non-regular language, yours and mine. Anybody remember our favorite example? You don't know yet that it's your favorite. It is your favorite. It can be your favorite even if you don't remember it.
Was it A to the N, B to the N?
A to the N, B to the N is not a regular language. And we did a proof of this, which was somewhat laborious and very much purpose-made for that specific language. But you will see this proof is very generic, like you can imagine doing the same argument for lots of different languages. So A to the N, B to the N is not regular. All right, we're going to have to do a tiny little proof here, although when you do these examples, the strategy of your proof is basically always going to be the same. You have to tweak it from one example to another, but you don't have to have a big new idea to do different versions of this same proof. What I'm going to show is, so we'll show that, can I call this L, just so I don't have to talk about it? I don't have to write that again every time. We'll show that L has infinitely many derivatives. What you have to do is think of a whole bunch of different derivatives that you could possibly take here. such that you will actually get a different answer every time. That's what we need to demonstrate. And in this example, and you'll see, we're going to do a lot of examples, so you'll see where I got this idea from. I'm going to say well, maybe I'll just say this informally first of all. Our different derivatives will be, one is the derivative with respect to a, one is the derivative with respect to a squared, derivative with respect to a cubed, etc. It turns out when you do each of these derivatives, they will always give you a different answer. And that means there are infinitely many different derivatives, and so the language is not regular. So the way I'm going to write this, the reason I chose these is because the strings in this language consist of a whole bunch of A's first, followed by a bunch of B's. And so I want to try to cancel off some of those A's. This first derivative will cancel one A from the beginning. This will cancel two A's from the beginning. This will cancel three A's from the beginning. And the results will all be different. But anyway, I'm going to say in general, let di be derivative with respect to a to the I of L. And these are going to be a bunch of different languages, right? So D1 is derivative with respect to A. D2 is the derivative with respect to A squared, and so on. Then, can anybody say, what is DI if you write it as a set? It means you start with this thing, but basically you cancel off a bunch of the A's on the front. How many? I of them. What would it look like then? Yeah?
A to the n minus I, b to the n.
Yeah, a to the n minus I, b to the n. All right? So what I'm talking about here is a set of things which have a bunch of A's followed by a bunch of B's, and the amount of A's is I less than the amount of B's, right? So these have number of A's is I less than number of B's. All right? And wouldn't you believe it, those sets, DI, they are all different from each other. Like D1 is the one where there's one less A. D2 is the one where there's two less A's. D3 has three less A's, right? They're all different from one another. So these DI are all different. And so L has infinitely many different derivatives. That's what we were supposed to show. Yeah?
So why is this different from before when we were like, oh, a to the n is still a to the n? Like, wouldn't that same logic apply here where it's like, oh, we have any number of a's, so then like, you'll still have a bunch of a's?
Yeah, this is a good question. It's true that what you started with has a bunch of A's followed by a bunch of B's. But they are in a very specific relationship. They have the same number of A's followed by the same number of B's, right? And when you take these derivatives, you're taking away some of the A's, but not any of the B's. And so when you write it again, it has to look like this. The amount of A's is no longer the same as the amount of B's. And so you might be tempted to wonder, maybe that's actually the same as a to the n, b to the n. Because it doesn't matter, this is like in the examples we were doing before. You take away some of the A's, but you just still have a bunch of A's, right? But in this case, it's not. These are not the same anymore, right? Like this is one in which there's the same number of A's and B's, but that's not the same as this, in which there are fewer A's than there are B's. So those are not the same anymore. These really are different. These DI's are all different, and that means L has infinitely many derivatives, which means L is not regular language. All right? Not a regular language. I got just a few more examples, and that'll do us for today, I think. Any questions about that one first? This is like the standard example, everybody's favorite, simplest example. But, as you do other examples here, they're not all that, it's not all that strange. Let's try another one. How about this language? A to the n, b to the n, c to the n. Does it make any difference if we have another letter there? A to the n, b to the n, c to the n is not regular. I'm going to do exactly the same thing. Really, that C, because it's on the end there, on the right end, it doesn't affect anything about the proof that I just wrote, right? You can do the exact same proof again. Here we have a bunch of A's at the beginning, and so my derivatives that I do are going to be derivatives with varying numbers of A's. So I'll say let di, this is going to look almost exactly the same, right? This I call L. You take derivatives which cancel off some number of A's at the beginning. All right? And then what is this as a set? It looks like A to the n minus I, B to the n, C to the n. And again, those are all different. How do you know they're all different? As we've seen before, sometimes you can write the same set in two different ways, and it looks different, but actually it is the same. But here they really are different from one another because this set is one in which, I'll say here, the number of A's is, I'm just writing the same thing I wrote last time, is I less than the number of B's and C's. All right? And if you use a different I, you're going to get a different set there. So the di are all different. So L is not regular. Right? I wrote basically the exact same stuff. What if it was, we just did A to the n, B to the n. What if it was B to the n, A to the n? Same thing, only I would have taken the derivatives would be with respect to B. The reason I used A here is because A is on the front, and I wanted to cancel partially part of the front of the strings there. All right, 2 more examples. How about this one's slightly more interesting, but really it doesn't get terribly different from these examples. How about this? BA to the n followed by AB to the n. Now, you're going to have to change something a little bit this time. I no longer want to consider derivative with respect to A to the I, because these strings, they do not begin with a bunch of A's, right? They also don't begin with a bunch of B's, because they begin with like BA, 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 BA. So anyway. Anyone want to suggest how should I set up my derivatives this time? You're always going to just choose a bunch of derivatives with respect to something or other of L. You want to choose them in such a way that you get a different result every time. Yeah?
BA.
Yeah, I want the derivative with respect to BA to the I. All right? You cancel those BAs kind of one at a time. All right? And can you say as a set, what will that look like when you write it as a set? Yeah, BA to the n minus I. There used to be n of them, but I canceled out I of them, so what remains is n minus I. And then followed by AB to the n. All right? And those sets are all different. You should write something, at least something very simple, that explains why those are all different when you look at various I's. So I will say these are all different. Sorry, I'll try and write the same format as I've done before. So here, the number of BAs is I less than the number of ABs, right? Because here we have a block of BAs followed by a block of ABs. And in the set DI, there are I fewer. I suppose I should be saying fewer rather than less. It's fine. This kind of is a course about languages, not that kind though. All right, so the DI are all different. So L is non-regular. All right. This is a very slight variation, but it's still basically the same idea. All right. I got one more example. We got 10 minutes left. I don't think my one more example is gonna cover 10 minutes. Would it be all right if we finish early? I should have brought more examples, I guess. One more example. I want to look at what happens in this kind of argument if L was regular. You should get suspicious if I end up writing we just wrote basically 3 proofs which are almost all identical. You should feel like, is that always going to work then? Well, no, it can't always work because, like, not every language is non-regular. So it would be good to look at, what if L actually was a regular language? Where does that kind of thing break down? How about this? Slight variation, right? That one actually is regular. A to the n, b to the m. A bunch of a's followed by a bunch of b's where there's no relationship between the first part and the second part. This one actually is regular because you can make a NFA or a DFA out of it. How about here's a NFA? Just because I like them epsilons. There are other ways to write this. Actually, that second one is irrelevant. How about just this? That's a decent NFA for this language. Okay, so it definitely is regular. All right. So L, I'm going to say parenthetically, L is regular. I just want to see what will happen if I try to copy that proof. Like, at what point does the proof fail to work? All right. Let's see what happens. I'm just going to start writing. I will say let di be derivative. Now, since the a's come first, I'm going to take derivatives with respect to a here. Can anyone say, what is that? How do I write that as a set? Well, I guess just copying what we've all done so far. A to the n minus I, b to the n, right? Are those sets all different? Some people are shaking their heads. Actually, they are not all different. This is where the proof fails. In fact, these sets are all the same. This is related to something that he asked a few moments ago. You have thoughts about that? What can you say about these sets? Yeah?
Well, I guess I'm just confused as to the difference. Like, is it because there is no, like, relationship, like, you could still have an array as a A?
Yeah.
The number of A's isn't, like, defined.
Yeah, it's because the number of A's has nothing to do with the number of B's. So what I'm saying here, the original set, there's just some number of A's and some number of B's. This set, I say, there's some number of A's and some number of B's. It actually is the same set again. This, in fact, as a set, it is equal to this. Right? The fact that you took away I of them means, like, you imagine there used to be more A's, but now there's less A's, but it doesn't matter. There's still just some number of A's there, followed by some number of B's there. All right, so the conclusion here is these are all the same. So we cannot conclude that A is non-regular. And in fact, A is regular. That's why this didn't work. We cannot conclude that L is non-regular. So it's a little tricky to recognize that these sets are all the same, even though it looks on the surface, it looks very much like our previous examples, but it's not. All right. The same thing will happen if you try to do something like L equals A to the n. The natural thing to try would be dA equals this of L, which would be A to the n minus I. But that's just equal to A to the n again, right? And so you didn't get anywhere by taking all those different derivatives. The point is, you have to find infinitely many derivatives which give you different answers. In this case, and in the previous case, actually that's impossible. And you're not going to get any different answers. You get the same answer every time. All right. So this is what happens if you start with a regular language. If you're doing everything correctly, you will find that your derivatives you thought there was going to be infinitely many of them, but they're all the same, or there's only like 2 different ones, or something like that. All right, and I think that's where we'll leave it. I don't know if I mentioned, we're not having homework due today. That means we also are not having a quiz this week. We will be back to our normal schedule next week, so we'll have a homework on Wednesday and a quiz on Friday. See you Friday.